what we're going to do now is to use this expression we have for alpha to continue analyzing the z function. And what we are going to see after this analysis is that the error of a strong classifier is upper bounded by the number of weak classifiers that you decide to train. So first, taking the function z, we're going to substitute alpha here and here with this expression. We're going to get a larger expression, but the only thing we have done here is to substitute these alphas here. Okay, so that's why you have this expression inside here and here. And now let's simplify this. In the next slide, what you can see here is that you have this exponential and then it's multiplied by this natural logarithm. So these two will cancel out each other. So you will get only this expression here in this part. So this, we have the square root of this expression. We have cancel out the exponential and the natural logarithm here. And remember that the sum of the weights of the examples that are correctly classified is 1 minus epsilon. That's why we have written here 1 minus epsilon instead of this. And instead of the sum of the weights of all the examples that were misclassified is epsilon. So we have written here epsilon. From here, what you can do is to move this 1 minus epsilon inside the square root. To do that, we need first to compute the square of this. So we will have this expression to the square. If you do that and you move it inside, then you can cancel out this denominator because you will have this 2 times here because of this. And the result of that is that you will have the square root of epsilon times this expression here without the denominator. And you can do the same with this epsilon here. You can move it inside the square root, but squared, so you will have epsilon squared, and epsilon squared over 1 epsilon will disappear this epsilon, and in the end you will have 1 epsilon here, which is exactly the same that you will have here. That's why by doing that we can then have 2 times the square root of epsilon times 1 minus epsilon. Okay, so this is a way to compute this z function. We are going to now to introduce another variable that we are going to call gamma. Gamma is going to be defined as 1/2 minus epsilon. This is for a specific weak classifier t. And we can see that this gamma can take values in this interval. So if the error of our weak classifier ht is 0, then 1/2 minus 0 will be 1/2. So that's the maximum value that gamma can take. So this is 1/2. And if this epsilon is 1/2, remember that our weak classifier should have an error at least smaller than 0.5, but in the extreme case, suppose that it's a 0.5, this is going to be 0.5 minus 0.5 is going to be 0. But we write that interval here open because we know we will never get a 0, because this error can never be 0.5. It should be smaller than 0.5. So in the left we have an open interval, and to the right we have a closed interval. Okay, so these possible values for gamma are important in the next steps of our analysis. So in the next step, what we do first is to substitute these epsilons here with an expression of gamma. So epsilon will be equal to 1/2 minus gamma, okay, by moving this to the other side. If we have that expression 1/2 minus 1/2 minus gamma and you write it here, it is you should be able to do it yourself. You will get this expression here. Okay, you just need to write here 1/2 minus gamma, and also here 1/2 minus gamma, and you develop this. You apply the products and the sums, and you will get this expression here. So it's the square root of 1 minus 4 times gamma squared. Now, this expression here will be at most the same as this expression here, that is the exponential of minus 2 times gamma squared. Now, how can you be sure of that? Take, for example, the minimum value that you can assign to gamma, or gamma can be. So this value is 0. So in this part of the inequality, if gamma is 0, then this product is going to be 0, and you will have 1 minus 0, which is 1, and the square root of 1 is 1. So in the left side, to the left side, you will have 1. Okay. If you do the same here, you will have 0 squared is going to give you 0, times 2 is 0. So you will have the exponential of 0. And the exponential to 0 is going to give you 1. So in that case, you will have 1 here and 1 here. So at that moment, you will have this equality to be true. And if you take the maximum of this, 1/2, here to the left, you will have 1/2 squared, that is going to be 1/4. 1/4 times 4 is going to give you 1, and that is going to be 1 minus 1 is 0. So you will have square root of 0 is 0 here. If you have here 1/2, this is going to give you 1/4 times 2, that's 1/2 again, 1/2 negative. If you compute the exponential of minus 0.5, that's going to give you something like 0.606, something like that. So in the maximum here, maximum value for gamma, you will have a 0 here, and here you will have 0.6. Okay, so this expression here is an upper bound of this expression. Now, why is that important? Because you should remember that this is an expression of the error of the weak classifier T. If you apply this to many weak classifiers, we can see then that the error of this big H, which is the strong classifier, is the combination of all the weak classifiers, is Z, and this is going to be bounded, upper bounded by the exponential of minus 2 times gamma squared, but all the sum of the gammas, because we are going to train T weak classifiers. And what this is telling us is that the error of a strong classifier is upper bounded by this expression, where you have at T the number of weak classifiers. And as you increase the number of weak classifiers, this product here will be a larger and larger negative number. And as you do that, the exponential of this large negative number will decrease. So as you increase the number T, you will decrease the exponential. And that is a bound to the error that you can get with your strong classifier. So every time you add a new weak classifier to the strong classifier, you will be decreasing the upper bound exponentially. And this is a very robust result analysis or performance analysis of the AdaBoost algorithm. So a weak classifier with small error rate will lead to faster descent because of the exponential expression here. Okay. Now this is a plot of some comparison made by Shapiro and Corso. Here in this plot, what you see is AdaBoost implementation using as weak classifiers the decision tree algorithm, which is called the C4.5. And you can see how if you use only the decision tree algorithm, the error gets over here, like 14 error. And this was applied to a data set where the problem was to classify letters. So if you use only the decision tree algorithm, the error you will get is something like over here. But if you use that algorithm like weak classifiers in AdaBoost, then you can see here the training and the test error. As you increase the number of rounds or the number of weak classifiers, the error goes down. This plot is also important. So you can see what kind of error curve you generate with your AdaBoost. This is the kind of plot that you will generate when you program the AdaBoost algorithm for classification. Okay, so here are some references that you can check. And that's all about AdaBoost. So thank you guys, and talk to you later.